The goal here is to model everything in Python. I'm sure there are some ready packages to go with, but it's always better to have a deep understanding and to do everything yourself. So the goal of this course is to develop a Python simulator, which is going to basically model the single phase and multi-phase scenarios. I have some. In this class, I'm going to show in this course, I'm going to show the first the equation that we are solving numerically, and then I'm going to show some of the analytical solutions that we are going to use for the benchmark. And then I'm going to show what to expect from the numerical simulators in terms of the maps, pressure maps. And I will be really happy to hear any questions at any stage. Okay, if you have any question, just stop me and ask your question. And I believe that way it will be more interesting. If you have any question, just ask. Okay, stop me and ask. So do you have any question at this stage?
No, it's fine.
Okay, so let me start with first introducing the equation that we are going to solve numerically. So for the single phase flow, let me see. Okay, for the single phase flow, we have this diffusivity equation that we need to solve in the radial coordinates. Okay, first, this is the equation. This is the general equation for the radial coordinate system. And this type of flow can best describe the flow around the wellbore. Okay, but we are going to use the Cartesian coordinate system mainly. But the equations, the solutions can be compared. Like in the numerically, we are going to use the Cartesian coordinate system to solve the problem. But the analytical solutions, some of them are available in the radial coordinate as well. And that's why we are going to compare the results should be the same. Okay. It doesn't matter which coordinate system you're using. So this is the general equation shown in the radial coordinate system. And we in the fluid mechanics class that I'm also teaching in this semester, we have introduced the two-stage solution for this two-stage conventional solution for this problem. So we have the transient solution, which is commonly discussed in the reservoir engineering class, and also we have the steady-state solution, which is also discussed widely in the reservoir engineering classes. So, first solution is the assumption of the infinitely acting reservoir, and the solution is given with this equation in the SI unit system and with this equation in the field unit system. So we will need this equation for the transient flow comparison. Okay, and we need to make sure that our time interval is in between this times, the endpoint times. Like initially it's affected from the wellbore conditions. Later, it's affected from the reservoir boundaries. Okay, so we need to make for the infinitely acting reservoir, we need to make sure that our time is in between this region. Now, the other question, the other solution is a steady state solution where we have the boundary affecting the flow. Okay, this is the solution for the steady state solution, and this CA is the shape factor which is available in the form of table. Okay, we can use the table. I don't know why I can't see this table now, but we have this data available. So in the stage when we have the numerical solution ready, we will be able to compare that steady state solution and our numerical solution. Now, all this step is numerically solved. Okay, and another interesting solution will be the green solution, which really doesn't divide the solution into two parts. So we can use this. We can use the green solution at any stage. Okay, and the assumption here is that the reservoir is homogeneous. That's the same assumption that we have for the previous solution. And it's basically using the green sink and green source terms in order to calculate the pressure at any point given in the reservoir. Okay, and then it's implementing the superposition principles in order to include the multiple effects coming from the multiple sinks or source. Okay, and our sinks and source are mostly either injection well or production well. And the green solution as well available. So we may also compare our solution to the Green's function, okay, green solution that we have for the same problem, exactly the same problem. Now, about about the, so this is the solution. I showed the equation that we are going to solve, and also I showed the solutions that we are going to compare. But these are all solutions for the single phase flow. Now, in the case multi-phase flow, we had the Buckley leverage solution, which we are going to use in for the comparison. Okay, and in the Buckley leverage solution, we are going to simulate the scenario where we have the two immiscible flow, and both of them are going to be incompressible. And basically, we are going to, in the case when we are validating our model to the multi-phase flow model, we are going to compare it to the Buckley leverage solution. Okay, and Buckley leverage solution is in the semi-analytical form. And I can show you one scenario, one animation that best describes the Buckley leverage solution. Let me see. So this is the solution basically, and from the left side, we're injecting water to the reservoir, which is saturated initially with both water and oil, and water can be in the irreducible level, or it can be, we may have some initial water saturation which is higher than the irreducible water saturation. And on the right hand side, we're basically producing. So this is a two-dimensional problem, and we are going to generate the 2 degrees for the solution of this Buckley leverage case. And we are going to, our numerical solutions should match this, identically match this solution that we have for the for this Buckley leverage solution. Okay, that's the, so in the single phase flow, we are going to use the conventional models that that's used for the typically used in the reservoir engineering classes. And in the case when we are validating the multi-phase flow, we are going to include Buckley leverage solution for the benchmark. Okay. Now, let me briefly discuss about the numerical stage, necessary stage. So we are going to implement it in Python. So everything, and we're going to like have a live coding session where we are going to build our model. Now, about the finite element, the finite difference implementation of the numerical solutions, that's the way we are going to go with. So for the finite difference, we have different scenarios for taking the derivative at the given point. We are going to use the central difference technique on the second h-square order. Okay. So we are going to use this equation for the derivatives for calculation of the derivative. Because we have the Laplace term on the diffusivity equation that we need to use. So we need to use the second order derivative, and we are going to use this equation mainly. And this equation is going to be used to generate the transmissibility matrices. And basically it will be in the first in the vector form, and then we are going to combine them in the array form. And then we are going to use the linear solvers that Python provides as in the SciPy module. Then we are going to use those linear solvers in order to solve the final stage. And most importantly, our solution is going to be time dependent, which is the main crucial part. And we are going to use only the for loop only for the times. Okay, otherwise we are not going to use any for loop, because for loops in Python are very slow, as it's the same for MATLAB as well. So we are going to use basically at the initial stage, we may write the for loops for the filling the matrices, but then we are going to avoid we are going to replicate the same scenarios with the vector operations. Okay, we don't need to go with the for loops in order to fill the matrices, but for the time analysis, it becomes important to use the for loops because it's a sequential calculation. So every next step is dependent on the previous step. So we need to first calculate the n step in order to get the n+1 time steps. We are going to solve for the n+1 time steps. And the other thing regarding the numerical solutions is in the simple scenario, in the single phase flow, most probably we are going to go with the implicit solutions, because implicit solutions are more robust than the explicit solutions. So this implicit term, we are going to introduce why we are using this implicit term. Basically, it's only because we are using the n+1 time knowledge in order to calculate the n+1 time. Okay. Otherwise, in the explicit solution, we are using the n time step knowledge to calculate the n+1. Okay. That's the main difference between the implicit and explicit solution, and that's the main reason why explicit solutions are are not robust, and it can diverge in the scenarios when we don't have the proper grid sizes. But implicit solution most of the time converges with any given grid sizes. Now that's one important term for the simulators, okay, implicit or explicit solvers. So implicit solvers are like, we are going to show why implicit solvers are better, and we are going to continue mostly with the implicit solvers. Now this is the main part for the differentiation part, and we have generated the necessary script for doing this operation in Python. We are going to go over once more time. It's simplified. The calculations will be shown. So because this is the main function that we need in order to take the derivative of the functions. Now let's move on to the real 2D solvers, numerical solvers. Okay. First, we are going to generate the grids. This is the slides from the time I took the class, numerical reservoir simulation class, and its author is Dr. Balhov from the UT Austin again, and I just wanted to make sure that I mentioned his name because I'm using his slides in this scenario. For this scenario, so this is the 2D grids. Okay, we are going to generate a simple scenario. In this case, we are going to have 9 cells, which means that our matrix is going to be 9 by 9 side. And we have nx equal to 3 and ny equal to 3 as well. And we have the certain boundary conditions implemented at the edges of the reservoir. In this case, we have the so there are two different types of the boundary conditions we can implement in the finite difference numerical solvers. One of them is the Dirichlet boundary condition. The other one is the Newman boundary condition. Dirichlet boundary condition explicitly states the pressure at the boundaries. But in our case, we are going to have the unknowns at the center of the grid. So that's the reason why we are going to have like in the case when we are implementing the Newman boundary condition, we are going to still have even in the Dirichlet boundary condition, we are going to still have the 9 unknowns, but we are going to modify the boundary values, basically the cells at the boundary according to the boundary condition that we have. Okay, and our grid solver can also solve this scenario with any type of boundary conditions that we have. So like initially we are going to have a simple case, this simple 3 by 3 grids reservoir, and then we are going to complicate it a little bit more just by adding more wells and more dimension to the reservoir. So 3D solver is basically just a mathematical manipulation of the 2D solvers. The idea is going to be the same. So first we are going to start with the 2D, and then if important, we can just modify some of the functions that we are going to use to generate the 3D matrices. So if you have the 2D solvers, you can easily modify it to make it 3D solver. Okay? It's not a big deal. Now, regarding the wells, we are going to specifically show how we are going to modify the transmissibility, the matrices that we are getting at the end of calculation for the production well, for the injection well. And for the boundary conditions, we said that in the well, we might have a constant pressure condition, and also we might have a constant flow rate condition. It's the same for the numerical solvers as well. We can implement different boundary conditions on the wellbore, and we are going to get the scenarios for both types of solution, and we are going to compare to the analytical solutions accordingly. Okay, we are going to show how we are going to modify our matrices with the different boundary conditions that we have. Now, this is the reservoir input we can have for the solver. The other important thing is the relative permeability curves, and like most of the time, like probably you know that our numerical simulators are very sensitive to the relative permeability curve types that we are selecting. So we are going to stick to the one model, which is shown here, and we are going to use this model. And we are going to use this. This is going to be a separate function, where we give the saturation information. We are going to get the relative permeability values, and we are going to use that in our calculations accordingly in the transmissibility matrix, especially. So there will be some basically some terms that's important for the solution, and this d is one of them. And you are going to see how we are going to use this d value in order to solve the main final form of the linear system of equations. Okay. Now we said that we are going to go with the stick to the implicit solution solvers only mostly, and the IMPES method is basically implicitly solves the pressure and explicitly solves this saturation. Okay, that's this abbreviation for. Okay? Because like I said, implicit solvers are robust, but there are some downsides of the implicit solvers as well. So so we are going to understand it better once we discuss it into like in detail. Once we discuss them in detail. Okay. Now since we have the 9 cells in this given reservoir, we are going to have 9 equations basically. And 9 equations means that we need to include, like whenever we have the well in the cell, we need to include those Q information into our matrices as well. Okay, we're going to go over this calculations, and these are the necessary calculations for the generation of the proper form of the equation, and then we are going to see how this equation combines into the matrices where we're having the final set of the equations. Okay, we are going to go over the every cell one by one, and we are going to write the equation, and then we are going to see how this equations combines to form the final form of the matrices. Okay, so you see we're basically solving all the generating the equations separately for each cell. Now this the other thing is related to wellbore as well. So like we need to do some modifications to the cells which has the wellbore, and we need to do some correction types. Okay, this is the final form of the matrix that we are going to get final form of the transmissibility matrix that we are going to get. Okay, and we are going to discuss all this in detail when we start to solve. Okay, and the solution is given for this scenario as well. So P0 is initial pressure is given 1000 psi, and then we are going to calculate the pressure at the second time step. Okay, this solution we are going to make everything, like prepare everything in such a way that we will be able to modify just few variables, and then we will be able to change the number of grids that we have in the reservoir. Now that's mainly it for the multi-phase solver. So we have this solver. Basically, given these values, you will be able to like code everything yourself and to get the same values that we have here. Okay, so that's for the IMPES way of solving implicit pressure, explicit saturation. Now SS method is basically we're implementing the same idea in a different way. So if we are filling matrices in a different way, we are going to go over the details. We should ideally get the same solution. And as you see, almost identical, like results are almost identical to the IMPES solution. We are going to discuss this 2 type of solution. Okay, basically in the code, we are going to just modify 1 or 2 lines, and we will be able to get the result for the SS solution as well. So this is the multi-phase flow scenario. Okay. Now, but first we are going to start with the single phase flow, and we are going to its single phase flow is a bit simpler than this one that we have here. Okay, and then we will switch to the multi-phase flow and then do the comparison to the Buckley leverage solution. Okay, so so that's mainly the idea of this course. Okay, if you have any question at this stage, just please ask. So this is the introduction part, okay? And basically from next week on Saturdays, we are going to come together and start coding together and start to implement everything step by step in order to get the final form of the solver. Do you have any question? So if you don't have any question, this is the final result that we are expecting to get from the solvers. This is the reservoir boundary defined in the input, okay, and then we are going to get the maps for the pressure, and also we are going to get the saturation info for the at the given time steps. Okay, and like if you're doing everything correctly, then we can also on the same time compare this solution to this CMG solution, and it should ideally match. Okay, but as I said, initially the first goal is to get the single phase solution, and then we are going to basically compare the single phase solution, and then we are going to try to numerically solve for the backward level scenario, and then we are going to go with the more sophisticated multi-phase scenarios. Okay, and we are also going to discuss about the speed performance of the solver as well. Okay, so that's the final expectation from the output of the simulator. Okay, to get the pressure maps and saturation maps for the multi-phase scenario, only pressure map for the single phase scenario. Okay, so that's pretty much it. If you have any question, I will be happy to answer. If not, I'm going to see you next week. We are going to start to code together.
If you have a question, you can type in chat section, or you can raise your hand and ask with voice.
So let me ask one question here. How many of you are using the Python right now?
Mr. Javid, actually, there's a question chat section. Okay. I can read for you. Rasul Amirov asked, in general, which year students must be able to know it?
So if you are if you have taken the reservoir engineering class, you should be able to bear with me. If you have the basic understanding of the reservoir flow, then it should be fine for you. Because the equations that I showed is from the reservoir engineering. It's introduced in the reservoir engineering classes. Okay, if you are familiar with the analytical solutions, just familiarity will be sufficient. Because I'm going to show the equation as well. But you need like at least a fundamental understanding regarding the reservoir flow in order to understand the numerical solution as well. Can the attendees ask questions directly?
Yes, they can unmute themselves.
Okay.
But I guess, okay, we have another question. Typhoon Jamal Bada asked, will we learn how to basically simulate reservoir in this course?
Yes, that's the goal. That's the goal here. I mean, we are going to develop a model, like we are going to use Python and script, like, write everything step by step in order to get the solution, numerical solution for any given input. Okay, we are going to first solve the single phase scenario, and then we are going to solve the multi-phase scenario. So the other question is in which dimension, 1D, 2D, or 3D. So as I said, our numerical solver is going to be 3D, full 3D. But for the demonstration purposes, we are going to write everything in the 2D. And as I said, 2D is not much different than the 3D. It's just going to, like, you are going to, like, if you write everything correctly, like when you're coding, if you consider the 3D scenario, which we are going to do, you can just modify it a little bit, and then simulator will be the 3D simulator as well. Okay, so the modification parts come to only the transmissibility matrix that we are generating for the solution. So we are going to write in such a way that just like switching to 3D will be just a matter of seconds.
Okay.
Any other questions?
I guess there is no more question. Okay, we have Shashwat Harsh asked, what level of Python required for this course? Is basic Python is enough?
Well, that's the question I wanted to ask. Okay, I'm expecting you to some fundamental understanding of the reservoir engineering, basically reservoir flow. But if you are not familiar with the Python, I can like for an hour or so, I can just introduce the Python. I can show you how to download the Python and how to install if most of you is not familiar with the Python. I can show you how to download it, how to install it, and then how to start to use it. Okay, there are three important steps. But since you asked, I'm just going to go briefly show how to download the Python. Okay, I'm assuming that most of you are using Windows machine, but it's not very much different for the Mac machine. And for the Linux system, Python comes installed already by default. So if you have a Linux machine, you have the Python in your computer. But if you are using Windows or Mac, you can just go to the Python org. Okay. And then download the version which fits to you best. This is the most suggested version, the most recent version of the Python that you can download for the Windows. Okay, just make sure that you have the correct version of the Windows. Yeah, you are just checking the whether you have the 64 bits or 32 bits, and that you can do from the going to settings of the properties of the computer, and you can check whether you have the 64-bit operating system or 32-bit operating system. Okay, if somehow this version doesn't work for you, if this version works for you, you can just click on that, and then the download will start, and then you can go with the installation. But if this version doesn't work for you, then you can select the operating system that you have, and most of you probably will have the Windows, so I'm going with the Windows. And then it will direct to the versions of the Python that you can have for the Windows. Okay. Sorry for this slow internet I have on my PC. As soon as it opens, I will show you which link to click. Okay. Now you can select the correct version of the Windows for your machine. You can go with this is the 3.9.4 version, which is the most recent version, but you can install the previous versions as well for your Windows machine. If you have the 64-bit operating system, this is the link you need to click. And then you can just make sure that you have the version 3, okay? So this first number is the most important thing, okay? If you have, I mean, it's not going probably to cause much difficulty if you have Python 2, so it's going to be okay. But it's better if you have the Python 3, okay? Just make sure that the first number that you have is the 3, okay? That's it. And then you can install any previous version, okay? And then after the download, you will be able to install. And I can send you one link which you can follow in order to for the installation, okay? Installation part is not a bit tricky. You can go with the default version, that will be it. Okay, after installation, you will need to set up some of the modules that you're going to use, okay? For that, you can go to the command prompt. If you have done everything correctly, okay? If you have Python installed correctly on your machine, when you go to the command prompt, just type the CMD in the search box and you will pop up the command prompt. And if you type the Python, it's going to mention the version of the Python that you have, and you can start the coding, okay? Now, I'm inside of the Python, so I can write pretty much anything. A is equal to 5, and if I ask what's A, it's going to give me the 5, okay? This is the Python, and it's installed. If I want to exit Python, I'm going to type exit and open, close the brackets. Now, so if you type the Python and if you get this step, then it means that you have working Python and everything is set up correctly. Then another thing you need to do is to pip install numpy, okay? And if you type this pip install numpy, and if you click enter, then it will start the installation. Since I have the numpy in my machine already, it's going to say that requirement already satisfied. But in your case, it's if you see the successful installation at the end, it means that there is no problem with the installation, okay? Then the other library that you need is the pip install matplotlib. That's for the NumPy is for the array operations that we are going to do. Matplotlib is for the plotting purposes, graphical plotting purposes. And then the other thing you might need is the SciPy. Okay, just type pip install matplotlib and then click enter, and then type pip install SciPy, and then you'll be ready to go. And if you need any other module afterward, I will just ask you to do the same thing for that module as well. But most of the time, NumPy, SciPy, and Matplotlib is sufficient for this Python. And if you want to start to code, okay, you will just type the idle on the search box, okay, and then it will direct you to the interface that we have, like free interface that we have for the Python, okay. And then we are going to go like code everything on this idle shell, okay. And I'm going to code myself on the idle as well, okay. You will be able to follow me. If you have any problem with the installation of Python, or if you are not familiar, and if most of you want to have a Python introduction to Python session, then we can do it for an hour maybe next week. Okay, just let me know. I mean, just let the moderator to know that you want the Python session. Then we can do it. Like I have some ready slides. I can use it for the introduction of the Python. So which libraries will be used in the Python? So basically, I said we're going to use NumPy, Matplotlib, and SciPy mainly, but we may need other libraries as well. But I will let you know beforehand. Okay. The other question: is there any additional package for simulation with Python? I mean, are the Python functions the same for reservoir simulation? Well, we are going to write everything by ourselves. So Python functions are going to be sufficient, and we are going to install another libraries in order to do the necessary calculations for our reservoir simulation purposes. What about Google Colab? Can it be used? Well, you can use it. If you are happy with the Colab, you can use it. I'm not asking you to use the idle shell necessarily, okay? If you can code the same thing in the Colab, it's up to you. I mean, it's not mandatory to use the idle shell. But by default, I'm going to go with the idle shell. I'm comfortable with that. Okay, so I think that's pretty much it about the Python. And I don't really expect you to have the very deep knowledge regarding the Python. Okay, if you have installed it and if you have the Python version ready on your computer, you will be able to keep up with me in this series of course. Okay. Any other questions?
No questions, I guess. If there is no, we can end up our session if you want to still tell it. So thanks for this great presentation and introduction. We will meet again, I guess, the next Saturday.
Yes.
So if you have addition, you can say.
Thank you very much, Hussein. Yes. Well, we will meet next Saturday, hopefully. Just let me know if I need anything else to provide. But if you have any question, like from the people attending this session, if you have any question, just let me know. I will be available for the questions. And thank you very much, Hussein. I will hopefully see you next Saturday as well.
Okay, thank you very much too. So, okay. Thanks. Thank you very much. Thank you.
Thank you, guys. Thank you.
See you.
See you.